Welcome back, everyone. Hope you're all having an amazing day. So in our previous video, we looked at how to use cognitive search to retrieve information from your own data sources and then pass it on to ChatGPT for inferencing. That was one method. There's a second method, or the more common method, is to use vector embeddings, a pure vector-based search where you convert the user query into a embedding vector. And then you would also have a vector database that has all of your documents converted into vector format. And ultimately, you perform what's called a cosine similarity search against the user query against your vector database. And you would retrieve, say, top 5, top 6, top n documents, and then pass on those documents back into ChatGPT for inferencing. So today's video, I'm going to cover the basics of vector embeddings. And here I'm just referencing a blog here, and vector embeddings can be from various different sources. For example, you can have an audio as audio model, you can have a text model or video model, so different models. The most common one currently would be the OpenAI text ADA embeddings model that converts text into vector embeddings. And similarly, there's other models that can convert audio into embeddings and video into vector embeddings as well. So in a nutshell, it's the same methodology. Whether you have audio, text, or video, you would still pass on whatever incoming query into that vector format, convert it into a vector, and then perform search against your database. And that's not the only application. We have many other applications that are possible. So for example, on the OpenAI website, the most common use cases for embeddings are clustering, search, recommendation systems, anomaly detection, diversity measure, and of course, classification. So lots of different use cases, but search seems to be the hot topic at this time. So looking at the OpenAI documentation, there are many embedding models, such as DaVinci, Curie, Babbage, Ada. And if you notice, the text embedding Ada 2 model is the best performing version because in terms of price and performance, it simply outperforms the other models. So you get about 3,000 pages of vector embeddings per dollar, whereas DaVinci is significantly more expensive. And if you look at the performance, so Beer score is a way of benchmarking retrieval, information retrieval. And score is very close. So naturally, the best model to use would be the text embeddings Ada version 2. And another important information to note is the older model. So the Ada embedding version 1 model has a max input of about 2,000 tokens, whereas the embedding 2 model, Ada 2 model, has about 8,000 tokens. So it's significantly, you can fit in a lot more information and retrieve the embeddings out of it. Although it's not a big limitation, you can always retrieve, you can always chunk the documents and then generate these embeddings on larger documents. So that's not too big of a constraint. And the output of this model, so when you pass on some text information, the output is a vector. So we call that the vector embedding is what's returned. In our case, the vectors are simply float point numbers. Basically a list of float point numbers that capture some kind of semantic similarity or semantic information of a statement, word, or a document. And then the max output length of that vectors would be 1,536 float point numbers. And that's fixed regardless of whether it's a word or several paragraphs. And yeah, so let's take a lok at the deployment. So this is the Azure OpenAI Studio portal. And here I have several different deployments. So I have the GPT 3.5 Turbo model, bunch of different text completion models. And finally, the one that we're going to be working with today is the text embedding Ada 2 model to retrieve those vector embeddings. Okay, now the best way to learn about vectors is to actually apply them and work with them hands-on. And what you're looking at here is an example of a Jupyter notebook with some code samples that I have to demonstrate how vectors work and how vector similarity search works. So this is an IDE called VSCode, and you can run all your various different programming languages like Python or C#, whatever you want to use. But in this case, I have an extension that loads Jupyter notebooks. And here in the first cell, I'm importing a few libraries, and these are the operating system, which is OS, OpenAI, which you will need to connect to the OpenAI endpoint to make that model inference. Whether it's through embeddings or even ChatGPT, whatever the model is, you will need that library. It'll make life a lot easier rather than working with REST APIs. And we have Pandas, which is used for working with data frames, and of course NumPy for working with arrays. So in this first code, what I'm doing is applying, setting the API type. So I'm using the Azure deployment of OpenAI, not the OpenAI.com. So I'm passing on the type of API that I'm using, and the Azure and the OpenAI.com APIs are slightly different. So you would need to double check which deployment that you have. And here I've masked the OpenAI endpoint and the OpenAI API queue, obviously. I'm retrieving them from the operating system's system variables. And I also have another function, which is get embeddings. Basically, it's a pre-built function that you pass on two variables, such as your model type, model engine, and the text, and it retrieves the vector embeddings. So let's try that. Let's run that function. I'm passing on the embeddings to a variable called vector, and let's see. And then the text here is single word orange, and let's see what the vectors look like. So there you go. So we have a list of float point numbers, and it's very large. Just for single word, you'll always, even if it's single word or many paragraphs, whatever it is, the length of the vector is going to be 100536. So 536. And this is the fixed length for this particular model. So depending on the type of model that you're using, you may retrieve different length of vectors. Okay. And obviously, if you want to visualize this in a text editor, we can certainly do that. So as you can see, these are all float point numbers, and there are 1,536 of them from this text data embeddings model. Okay, so in the next cell, we have a variable called vector2, and we're going to do the same thing, get embeddings for the text, which reads, orange that I am eating is very sweet and delicious. So let's see what the output looks like. There we go. Again, we're not displaying all of the output because it's just too large to display in this interface. And let's take a look at the length of that vector, and you'll see that it's also 1536. Now let's add a few words and let's treat them as documents. So I'm creating a data frame, pandas data frame, and I'm going to have a attribute or column called documents. And in this case, the documents are just simply single words such as banana, orange, hamburger wings, cheese, milk, etc. So we're going to assume these are documents that we want to work with. Okay, so 15 documents. Now, in this cell, what's happening here is we're using the lambda function to apply to every single row of this data frame. So you can, at row 0, row 1, we're going to apply this lambda function. And this function basically, again, uses that get embeddings that we looked at previously. And essentially, really, like, we're creating another column called data embedding and then passing on the corresponding embedding for each of these words. So orange will have its own vector embedding, and the other words such as water, building, etc. will also have their own embeddings as well. And then we're passing on that into the same data frame as a new column. So let's run that. And there we go, the run completed. So when I visualize this data frame, I should have another column with the embeddings. And that looks about right. So we have the documents and then the corresponding embeddings. Okay, so now you might be wondering, so what are we going to do with this? Normally what would happen is you would store these embeddings into a vector database. However, in this case, all of the information is cached in memory in this data frame, right? It's working in memory. So we're just, for this purpose of this demo, we're just going to continue using it and not upload it to any vector databases. Okay, now this another function is the cosine similarity function. And it's also from OpenAI Embedding utils. You can import that. And cosine similarity is essentially a score of how close two vectors are related. So it compares one vector against another. So we could take, for instance, orange, and then compare that vector, orange vector, against the banana vector, and you get a score of how similar they are semantically. Okay, so let's import that library as well. It's complete. And here I am getting the embeddings for orange and storing it in a variable called orangevec. And then same for apple and sandwich as well. And the idea here is I want to demonstrate how you can use cosine similarity. Okay, so we have the cosine similarity, apply that cosine similarity to the orange vector and then apple vector, and let's see what we get. So we get a score that's 0.865 and a bunch of other numbers. So that's the score for orange and apple. So since they're the same, they're kind of fruits, and they're something that they're also very commonly consumed. So that semantic relationship between orange and apple is captured in that case. So let's apply cosine similarity for orange and orange. So you get a score of 1, meaning they're exactly the same because you're just comparing the same vector, right? All the data points in the vector are the same. So therefore, the cosine angle between the two vectors would be 0, and therefore the score would be 1.0. And if you were to compare orange with sandwich, you will get a score of 0.77. So orange and sandwich, they're both sort of edible, food groups, but a sandwich is obviously not a fruit, so a lower score than comparing orange with apple. And here, okay, so what we're looking at here is a simple diagram that I drew in a whiteboard, and it's just to demonstrate if these vectors, these 1,000 whatever float-point numbers, if they were to be reduced in dimension to 3D space, and if you were to plot these vectors, these would, obviously that's just a representation, it may not look exactly like this, but the idea here is that you have 3 vectors, one for orange, one for apple, one for sandwich, and then the angle between them would be what we're using cosine similarity for. So in this case, orange and apple would have an angle that is smaller than comparing orange with the sandwich. Orange and sandwich vector. And smaller the distance between the two vectors, that means they're more closely related, more semantically related to each other. And from our experiment that we performed, that seems to be the case, right? So orange and apple score was 0.86. The score from orange and sandwich was 0.77. So just want to reiterate that the angle between the two vectors, smaller they are, the closer they are related. But the score that you get from that utility, OpenAI utility, the higher the value of that score means more closely those two vectors that you're comparing are related. Okay, so now you've seen the example of comparing two vectors and getting the cosine similarity score between them. But the question is, how do we apply it to our database? So consider our data frame that we've been working with. If you recall, we added the words, all of the different words in our data frame, such as orange, bananas, rose, red, pink, so on. And that same data frame here, what's happening is we have a search term, and then we're getting the embeddings for that search term, and then using the lambda function again to perform the cosine similarity score against all the rows in our data frame. So let's run this code cell here. And as you can see, for all of our documents, the cosine similarity scores are being generated for each of our documents in our data frame. So if I were to change this term to, say, I don't know, house, let's see. So there we go. So the cosine similarity for house is 0.88 because it's related to building. So this is, in a nutshell, how you would perform semantic similarity search. Right now, we're just working with single words. How about we work with more realistic documents? So we want to work with actual documents in real life. Maybe in real life scenario, you maybe only have single words, but likely you can have documents with paragraphs, sentences, etc. In this example here, I've just embedded the logic of getting the embedding and then performing the search into a function. And this function is called semantic search. So it takes in a query and a data frame. Ultimately, we start with getting that embedding for that query, user query, and then we perform cosine similarity search. Right? We generate the cosine similarities, and ultimately we will get the top index. So here, the top document index, essentially using the NumPy argmax function to get the index of the top score. Okay, so it actually gets the index, not the score itself. And here we're just printing out the score, the document that we found, and the score associated with that document. So pretty straightforward, very simple function. So let's run that function. And the next part is actually getting a user query. So it's just going to work within VSCode. So it's going to, when we run this, the VSCode will ask us for a query. And in this case, I'm just going to type in orange once again. And you'll see that the top document was orange and the similarity score was 100% or 1.0 in this case. Let's run that query again. In this case, let's just say house. I'm just going to type house, example that I used before. And then top document relating to house would be a building with a score of 0.88. So very simple way to implement a quick search function using data frames. Okay, so now we want to work with more realistic documents. And so I've actually created a CSV file called documents.csv. And this document.csv has various different topics, random topics that are actually AI generated. So the code to generate that is here. So I'm using Text DaVinci to generate these different topics. And ultimately it creates 100 documents, 100 rows in a CSV format and saves it as a CSV. So very simple script that I ran. I won't run it again because it does take a while to complete. But ultimately what's generated is that document.csv file that we see here. And that's going to act as our document of our basically our knowledge base. Okay, so we have our various different documents here, and I'm just calling it vector DB in this case. And what we're doing here is once again creating that vector embeddings for each of these documents. And let's see what that vector DB looks like with the embeddings added on. So you'll see the same format as previously. You have the documents, and then you have the data embeddings associated with each of these documents. So we're using that same search function once again. So the semantic search function that we built previously. In this case, we just have longer documents. That's the only difference, and more of them as well. So let's run that function, and let's ask about healthy lifestyle. Healthy lifestyle as our query, search query. And then, so you get the top document back, and you have the similarity score associated with that document as well. So it reads, there are many benefits to living a healthy lifestyle. Some of these benefits include having more energy, feeling better mentally and emotionally, etc. How about another query? Let's try another query. Maybe I want to talk about colleges, right? College or university. So there we go. We get the semantic similarity score, and then there's a document talking about many things to consider when choosing a college. How about I type a different word? How about university? Let's see if tell me about universities. Looking for university guidance. Choosing guidance. Universities choosing guidance. Cool. So it does, once again, the similarity score is quite high. And you notice that there isn't, even though we mentioned college and then used university later on as our search query, because of the semantic nature, it is able to capture that context, and it does return back the similar document when about helping choosing a college or university. So that's basically semantic search in a nutshell. I know I'm using data frames. In real production settings, you'll likely have various vector databases like Redis cache, for instance, or some other vector database. But ultimately, this is the basis of all types of vector search. They perform similar ways. They may have different ways to measure vector similarities. Like I know cosine similarity is one method, but there might be many other methods that can be used. And yeah, hope you guys found this demo useful. And likely in the next video, I'm going to talk about how we can build an application, or rather use an actual vector database and then store them in a real vector database and perform search. But ultimately, storing them in memory, like we're doing now, like right, using data frames, is not too far off. But yeah, thank you all so much for watching. Hope you found all of this information useful. And please don't forget to comment, like, and subscribe. Thank you so much. Take care, guys. Bye.